a balloon if it's not like a ball?
How can we roll a balloon if it's not like a ball?
Maybe you have to roll it really hard. But yeah, it'll probably bounce in a weird way, right?
That's a good, like, does it need to be a perfectly round shape or can it be more balloon shaped?
Do you think we have to take that off?
Maybe, if you wanted to roll it really
ball?
Yeah.
Yeah, you
Probably,
have to probably
probably.
fix the shape of the sphere.
That's a good point. It does need to be some sort of sphere. Okay, thanks, Tita.
All right, so I'm gonna actually keep this guy. Well, yeah. So what is curvature? So we have to talk about curvature. This is something that has anyone here taken like calculus?
Yeah,
Probably.
probably.
So at the
Probably
very end
does.
of like BC Calc, you talk about curvature of like like plane curves. It's that kappa thing, right? It's the second derivative divided by whatever. And so like it basically measures how fast something is turning. Mathematicians have a way of doing that in higher dimensions. And just to give you kind of a quick picture of things, right? So we had our ball. Our ball is, I'm going to actually draw on it again. So if I draw kind of like the two basic directions, then they both go in the same direction, right? Both kind of turn in the same way. And you can, I mean, it's if you actually learn the...
I want the balloon.
You want the balloon?
Okay. Can you hold it for me and show everybody? So if you draw those lines at any point, then they go in the same direction. And so they have what's called positive curvature. And in fact, the sphere, the ball, is known for having positive constant curvature. It's the same everywhere, which you could probably believe that a sphere is the same at every point. Turns out that if you take a donut, there's always a line, and here's where kind of another coffee cup turning into a donut thing comes in. How can I make it this donut? Well, if I start off with a cylinder, okay, and let's actually take this line and we'll put it here. If I take a cylinder, and then I glue the ends, I wrap it around, glue the ends, I get my donut. And you can believe here, I mean, this is a straight line. It has zero curvature. And so the way curvature is defined is it kind of takes those two directions and it multiplies them. And so this direction, it might be curving in the a positive way, but this guy is curving in a zero way, their product is zero. So this actually has zero curvature.
So you take the two strings, right?
Yeah, you have to do it over like all strings in all directions, but,
Okay.
but the basic idea is, yeah, you take kind of like the two basic directions and see like, are they going in the same direction? Or are they going in opposite directions? And then like you cook up a number based on the product. But if one of them is flat, as you can see, like this line is always flat.
Then it's zero.
And so then it's zero because zero times anything is zero.
Okay.
And so we've seen something that has, the ball has positive curvature, this guy has zero curvature, and what about these guys? So I said that they're hyperbolic. And the reason that they're hyperbolic is that they have what's known as negative curvature. In fact, they have constant negative curvature 1. Or they could be made to have constant negative curvature.
Can they be made to have zero?
No.
Okay.
It can only, so this gets back to what you were saying. Like, what if I stretch it? So that changes the curvature. So like the curvature of a ball is based on the radius. So like the bigger the ball, it curves less in any, like if you imagine like the sun, right? So like the sun, a small angle of the sun moving down here means it's moved like, hundreds and thousands of miles in the air, right? So like if its radius is large, then small changes down here still correspond to big things there. Do you have a question or no?
Oh, no.
And so like that changes the curvature, but from like a geometric point of view, the geometry itself doesn't really change. Does that make sense?
Yeah.
Okay. So what do I mean by, how do you see that these guys have negative curvature? So let's start with kind of the standard example. So I'm going to erase our donut for a second. And we're almost there, actually, to understanding at least
This is closer than I've ever gotten.
Yeah.
I'm very excited.
I'm usually lost after the first 30 seconds.
That's correct.
So I want to draw two pictures to give you a sense of what negative curvature looks like. So the first is, I mean, they have like examples of this in various places, but. This one's dead, okay. So again, I apologize for my left-handedness. Okay. And I drew this on my paper just so I would remember how to draw it. So I try to kind of make these lines somewhat comprehensible. So you can imagine that this is kind of like a funnel, but it's a funnel that's stretched forever.
Like a long trumpet.
Yeah, like a long trumpet.
Okay.
All right. So what this is also has negative curvature, and let's think about why. If you look here, kind of we zoom in there, part of the trumpet is going this way, right? And then part of the trumpet is curving actually not that way, but it's curving this way, right? If you look here, this curve is this way, but the width of the trumpet is kind of going that way. And so if you kind of look at this one's curving here, this one's curving here, they're not in the same way.
If it's going like a fat curve or a skinny curve?
Well, it's kind of like,
Convex or concave?
yeah, exactly.
Okay.
One is convex and one is concave.
Okay.
And so the curvature is negative there.
Okay.
And the other example, which is kind of like the classic one from I guess,
If it's convex and concave, is it always negative?
yeah.
Okay.
If one of them is convex and one of them is concave, then it's always negative. If both of them are concave or both of them are convex,
It's always positive?
yeah, because like even if they're both negative, negative times negative is positive.
Cool.
And then it becomes arbitrary. Like
That's, I understand that.
convex and concave only become like relevant if like you can tell one from the other. If they're both the same, then like that's kind of that you can't tell like, well, is this convex or am I just in the wrong place? Okay, so this one is a little harder to draw. I'm gonna try to do it justice. Okay. Okay, so where I've drawn the dots, that's like behind the solid part that's the only kind of way we can draw. So if you look here, right, again, we have something going, like say, in this case it's convex, and then this one is going the opposite direction.
Okay.
And so here we have, they're not both going like a ball in the same direction, they're curving away from each other. So if you have points where it's curving away from each other, and if that's true everywhere, which you can check is the case here, then it has negative curvature. And it turns out that after you have one hole, if you have more than one hole, so any of these guys, and this gives you something forever, right? You can have as many holes as you want. All of these guys are hyperbolic. And the amazing thing, and this actually is relevant to my own research, is that like they may all look like this if all I care about is topology. But if I want to put, say, and here I've been trying to think over the weekend about good analogies, right? So I might look at all Americans the same, okay? But if I want to look at any other characteristic, all of a sudden they become different, right? If I say, look at their birth dates, right? So I may, at first glance, see all Americans in the same light. But if I look at their birth dates, then all of a sudden they become different. There might be a lot of them that are the same, that all have the same birth date, but there are a bunch that are different. And so if I look at these all just from what's called topology, then yes, they're all the same. But if I want to understand kind of how big they are, or some other structure, which is known as like kind of a Riemannian structure, which I'm not going to explain to you, but the point is that like, how can I dress these up? In how many different ways can I dress these up? And it turns out that there are 3G, oh, well, alright, since I'm not going to do
Other side.
Since I'm not going to do complex dimension, I'll do this. 6G minus 6 kind of different, like, dimensions worth of different ways of how I can dress these up with what's called a differential structure, which means like giving it a sense of geometry. How many different ways can I define, distance on this thing, right? Right now, right? It just has a rough shape. It has just like the skeleton of something I'm interested in. But I want to also give it a sense of geometry. I want to tell like what the angle is between, you know, two curves. I want to define distance. How many different ways I can do that? Well, it depends on how many holes there are, and there are 6g minus 6 dimensions worth of ways I can do that. All right? Now this is all the two-dimensional story. Here's what your grandfather proved was the following.
We're so close.
We are very close.
So that 6g minus 6 is only for two-dimensional.
Correct.
Thing,
Correct.
okay.
I mean, so these are all two-dimensional, and so for any
Yeah.
for any number of holes bigger than 1, so from 2 on, there are 6g minus 6 dimensions worth of like geometric structure that I can put on this thing.
Mm-hmm.
Right? So what that means is that like there's a 6g minus 6 dimensional thing out there that like kind of characterizes it.
Mm-hmm.
What your grandfather proved was this is the Mostow rigidity. This is actually what is known as Mostow rigidity. It says that if M is a, alright, I'm going to put words, some of them ignore.
M is for Mostow.
Well, M is actually for manifold, unfortunately.
So close.
Is a complete, so I'm going to put in parentheses the things that you don't need to worry about so much. Complete finite volume.
Yes.
By the way, the trumpet that I drew here in a race, that actually has finite volume because this thing gets so small that it doesn't.
Okay.
Mm-hmm.
Finite volume actually should be fairly simple. I mean, it has finite volume. You just have to understand that because the dimension is higher. So M is a complete finite volume hyperbolic manifold. Okay, so hyperbolic just means that, like, you know, at any point it has this this property that like curves on it are going in like not all the same direction. I can always get them to like go in one curves this way and one curves kind of in a different direction. So
You mean the curvature is negative?
yes,
Okay.
Convex and concave.
yeah,
Okay.
yeah.
That's what hyperbolic means?
Yes.
Okay.
So here's the statement. If the dimension of M is bigger than 2, okay?
Which is bigger than what we've looked at.
Yeah, so I showed you, the reason why this is so amazing is that after 2 dimensions, well, let me say if dimension is 2, then M is the geometry of M is determined by pi 1 of it. So that
Oh,
like,
we had the pi one before.
right. So basically, like the number of holes in this larger sense, that determines precisely all the geometry of it. There's no longer like, you know, some number of different ways I could put geometry on it. No, there is only one geometry. You tell me what this is, and there's only one way. Like, that's why it's called rigidity. There's no fluidity in how I can define a geometry on this thing. There's only one way. Okay, and that's why it's so powerful, because like whenever you have a statement like this, it means that like on the one hand the